talk that I'll be giving in 2 weeks. And DARPA is interested in this classical and quantum computing boundaries, and that's what the meeting is about. And so I think we all know about quantum computing, that there is such thing as superposition. Now, classical computing does not actually take in superposition, but you can use classical computing to compute in superposition, and my talk is to try to show what that involves. And so what I'm trying to do is come in front of people who know about quantum computing and things that I know very little about. I've tried to understand what goes on there and some idea, but I really cannot say anything about it. But that's not my job. Others will be there to talk about that. My job is to say, okay, there's another form of computing that is not what you usually think of, and it has superposition, and so at least superficially it should resemble what you are doing, and maybe there's some mathematics there that will help one of these areas of superposed computing develop and understand the other. So that's sort of my my intention in this talk. I will have about half an hour or 35 minutes to make my point. And it will be very helpful for me if you keep that in mind and give me comments about how to make that point more clearly, more easily understood. So why don't we then go? And so during this first half an hour, so please limit your questions. There's plenty of time to discuss afterwards and go back to slides that you might want to discuss and talk with us. So I will go to the beginning of the talk, and the clock starts running for half an hour. So now it is 10 minutes after, so about 20 minutes to I should be done mostly 20 minutes to 12. So, all right, here goes. I'm talking about computing in superposition in the classical domain, and I hope to make in this talk the idea of classical domain and superposition clear to you. And where does this all come from? The origins. The origins have to do with classical computing, which has been extremely successful in modeling the physical world. I would say one of the prime examples would be the man has been able to go to the moon and come back. That would not have happened with computers and their ability to deal with the physical and model the physical world. But this has also, this tremendous success has created the expectation that we should also be able to model computing as it is done by the brain. For instance, learning from experience and learning to communicate in language. But this really hasn't happened. It hasn't happened, although it has been attempted to since 1950s, early days of computing. And I'd say there the idea of rule-based artificial intelligence, artificial neural nets and deep learning, they all have attempted to do that, but have not been tremendously successful. Now, it turns out computing with high-dimensional vectors is an alternative to computing, just classical computing. And this idea really goes back to Tony Plate's thesis on holographic reduced representation, 1994. So I would say, as an answer to trying to understand computing, brain-like computing or computing that could explain cognition, I'd say it goes into early 1990s. Not that it hadn't been tried before, but this is what I think is really the first complete system that gives us some hope of being able to produce computing that models the brain's computing. The insight here is that many of our physical and mental traits, they correspond to properties of high-dimensional spaces. And here a few things to come to mind, like the robustness of perception, of memory, and learning. They can be explained by properties of high-dimensional spaces. Likewise, the similarity of concepts. They can be very nicely mapped into properties of high-dimensional spaces. And the idea is that you could actually base a new kind of computing, found a new kind of computing by computing with high-dimensional vectors. Now, this model of computing, it is different from linear algebra, which probably would be what you'd first try to identify it with. It's also different from neural nets and deep learning. And it combines aspects of statistical learning and aspects of dealing with structure, computation, and dealing with structured information. So HD is sort of short for high dimensional or hyperdimensional. And by high, we mean that the dimensionality is actually in the thousands. For example, the dimensionality that we would deal with would be something like 10,000. That's just sort of the magnitude you need to keep in mind. And the operations on these 10,000 dimensional vectors, that's the key, and that's what I will be talking about. It's interesting, the nature of the dimensions matters less. The high-dimensional vectors could be binary, or they could be bipolar, or they could be ternary, or real, or complex. So we're dealing with something that is very, very general or generic to high-dimensional spaces. Not any of those specifically, but all of them have these properties. But here I will explain them in terms of bipolar vectors, in other words, high-dimensional vectors of plus and minus ones. Such vectors follow the binomial distribution with the n equals 10,000 and the probability 1/2. And here is a remarkable property of high-dimensional vectors, and it's true of all of these high-dimensional vectors. Nearly all pairs are nearly orthogonal. And I use the word quasi-orthogonal or dissimilar. And statistical call this property as concentration of major. And then another thing is that the quasi-orthogonal vectors are very easy to come by. If we need one, we just generate one at random. Another thing is that the high-dimensional representation is error tolerance, so the robustness is built into this kind of system because of the high dimensionality. In the next slide, there's a figure of comparing a 15-dimensional and 10,000 dimensional binary distribution with probability 1/2. Here is the 15-dimensional, and here is the 10,000 dimensional binomial distribution. And so if in this, first of all, in this space being a binary or bipolar, every point of the space or every vector is similar in the sense that the space from it, looking at the space from any point of it, the rest of the space looks identical. And so you take any point, and so how far do you have to go before you begin to reach most of the space? In a 15-dimensional, you go about 1/3 of the way, and you already start having a considerable amount of points similar to it. Whereas in 10,000 dimensional space, you have to go to about 0.47, 0.50 is the half mark point, 0.47 before really much of the space is included when you look at it from any point. So the simula, the correlated, they cover the distances from 0 to about 0.47, and then by the time you are at the distance of 0.50, 53, nearly all of the space is included. So this concentration measure and this property of high dimensional space is very important when we consider computing with these high dimensional vectors. In the next few slides, I will go through 4 examples to give you an idea of how these vectors are superposed and a little bit of what the properties of the superposition has. So the first, we just superpose variable with its value. And the second one, we encode a data record where there are several variable value pairs. And then we use that as an example where we actually do parallel processing. And the last one deals with encoding sequences into a single vector. So example 1, superposing a vector x, variable x and its value. And this is called as binding. So here we have these 10,000 dimensional vectors, so plus 1s and minus 1. There's one for the variable x and the other is for the value a. They are both points of the same mathematical space. The binding operation is simply component-wise multiply. So minus 1 times 1 is minus 1, 1 times 1 is plus 1. So the composed vector that binds a variable to its value is the product of the two vectors, product taken component-wise. And it turns out this product is dissimilar to both x and a. So that's an important property of the product. Now from the product we can release the value and this is done by multiplying the product with the inverse of x. Now in this particular case the inverse is a vector itself, so when we do the x times the bound pair, we regroup the x times x as its own inverse, so we get the value from the bound pair, we get the value of the variable. And in a case that the product operator is not a self-inverse, then we just have to use the inverse operator. The second example deals with encoding several variable value pairs into a single high-dimensional vector. In traditional case, you have the variables that they are locations in memory, and then the values are in those locations. And see, I've imagined like each of those values takes 64 bits. So bits 1 through 64 would encode the value for variable x and so forth. But now how do we put all of that into a single high-dimensional vector? So first of all, as before, each of the variables, each of the values is represented by a random vector. And these would be called seed vectors. When you deal with random number generators, they have a seed. Here we have a seed vector for each of them. So these seed vectors then are represented by bold x, y, z, a, b, c. Now each of those variables and values will be bound together. So the x equals a is as was a few slides before. Y equals b. This is a similar way, and z equals c is done in a similarly. So we have had six vectors of ones and minus ones, and now we have produced 3 vectors of bound pairs. So the next step is that somehow we have to combine these 3 vectors, and here we have just copied. This is the x equals a, y equals b, z equals c vector. We add them, just normal addition, and then with majority rule we can get back into vectors of ones and minus ones, and that is the vector h. I mean, here variable h is now represented with vector h. And it turns out that this vector h, it is similar to each of the vectors that were added together. And that's an important property of the sum or addition operator. The result is similar to what has been added into that sum vector. Now there are some minor difficulties here. If in this case we have had 3 things added together, and so the sums are always non-zero. If the sum is 0, we need some sort of workaround, like choosing at random if we want to get back into ones and minus ones. Okay, so now we have encoded the 3 variable value pairs into vector h, and now we can ask what is the value of x in that combination of 3 variable value pairs. And this operation, a probing or unbinding, again, as before, we use the inverse of x and do the multiplication. So that corresponds to releasing a value from a attribute value pair. The result, however, is not exactly a, but it is approximately equal to a. So right now we have something that resembles the true answer, and to get the actual answer we have to have in the system an additional piece, and here it's marked with the associative memory, and its function is to find the nearest neighbor among all stored vectors. So it means that the associative memory would have stored vectors for a, b, c, and x, y, z in order to do this lookup or cleanup. But anyway, because of the high dimensionality, the closest to a prime is a with very, very high probability, and so that is shown here at the bottom line, that we actually, from this combined information, we can actually retrieve the actual value of the variable. Okay, so next thing is some sort of an idea of how you can process information in high dimensions in a parallel fashion. And here, just as think of trying to solve the problem. We're given a vector q, and it's a vector of 3 variables, involves 3 variables, x, y, and z. And then we ask, does that any of those variables, x, y, and z, does any of them have any one of these values, a, b, c, d, e? Now, the simple-minded way of doing that is that you just multiply a with x and compare, is it similar to q? No, and you multiply b with x, is it similar? You go through all those pairs to find out if the result is similar to q. If it is not similar, if none of them is similar to q, the answer is no. If one is similar to q, the answer is yes. Yes, indeed, one of the variables has one of those values. So that's this instance in here. But we can combine all of these questions in examining a product that is a sum of a product of two sums, where here all the variables are added in together, and here all the values are added, and then you take the product of those. Just like in ordinary arithmetic, the multiplication distributes over addition. Here also, in this case, the multiplication distributes over addition. So this product has all these terms: x times a, x times b, x times e, y. So it has all 3 times 5, all 15 terms are included in its product. And now, because it's a sum of products, and sum is similar to all of the components that go into the sum, this vector p actually is similar to each of those products. And so all you need to do now is you compare whether p is similar to q. If it is similar to q, then one of these, it doesn't tell which one, but it tells only that one of these variables, x, y, or z, has one of these values, a, b, c through e. And this similarity, the fewer inputs there are to the sum, the greater the similarity. Eventually, I mean, a sum can be of so many terms that you cannot resolve the similarity. But this at least gives you an idea of how you can combine several operations by dealing with these vectors in interesting mathematical ways.
So the search you can accomplish by doing p dot q. You're going to compute the inner product.
Oh, that's a similarity. Similarity would be.
P dot q and p dot q is high, then
If it is close, if it is significantly different from 0, if that dot product is significantly different from 0, then the answer is that one of those variables has one of those values. It doesn't tell which one, so to find that out, then it would be another kind of operation, and it too can be done with this kind of computing machinery. Now here's a fourth example, superimposing elements of a sequence. And as an example, just use short sequences of letters. It's called n-grams, letter n-grams. In that case, we have a dictionary of 27 random vectors, each one representing either one of the letters or the space we include in this space as a letter. The n-grams themselves, they are encoded as products of permutations. And as an example, the n-gram THE, three-letter sequence THE, here is represented by this vector. It takes the first letter vector and permutes it twice. It takes a second one, permutes it once, and the third as it is, and then multiplies those 3 vectors. And so it is the R is the permutation. And here I've made a picture of that. And in this case, the permutation is simply just a rotation. And so here is the vector for T, and it has been permuted twice. So vector for H is once, and E as such, and then you just again multiply column by column, and then you get this vector for THE. it has some interesting properties. It is dissimilar to all the letter vectors A, B, C, and it's also dissimilar to all other n-gram vectors, such as H, E, T. In other words, it is sensitive to the order of the elements. It's also, the n-gram do not need to be trigrams. It is dissimilar to tetragrams, pentagrams, individual letters. And the other thing, and this is to me is more interesting and important and thought-provoking, this n-gram vector can be factored into its components using the inverse operations. And so THE was T permuted twice, H permuted once, and E taken by itself. So if we want to find out what the second letter is, we take the high-dimensional vector for the trigram, and then this cancels out the T, this cancels out the E. Here again we use the fact that the multiplication is a self-inverse, or that vectors are self-inverses with respect to multiplication. And then the final step, since H appeared in a second position, we have to counter-rotate. In other words, the inverse S is the inverse permutation of R. So things that can be packaged into these vectors that look very random, and then with the inverse operations, they can be, again, factored into what went into them. Sometimes it's exact, like in this case. If the inverses are approximate, then the result is approximate. It has to go through the associative memory to actually find the answer. Now, next I want to just give you the vocabulary I have used, and it gives you an idea of what kind of mathematics we're talking about. And I call it a laundry list because I'm just going to go through this very fast. First of all, there are three operations. Three. One is addition, one is multiplication, one is permutation. If you think of normal arithmetic, it's done with two operations. There's addition and there's multiplication. So here we have a third operation that interacts in an interesting way with the other two. And here's some of the properties of these. First of all, these operations preserve vector dimensionality. And then the vectors can be compared for similarity. And if vectors have a similar meaning, then they should be similar vectors. And the similar is based on a dot product. And the third property is that randomly generated vector is dissimilar, quasi-orthogonal, to all vectors that have been defined in the system up to that point. Now, a few things about the operations themselves. Addition is approximately invertible. Multiplication, it distributes over addition. It's invertible and preserves similarity. Permutation distributes over both addition and multiplication. It's invertible and preserves similarity. And all of these properties were used in the examples that I have shown so far. And here's an interesting fact to note, and that is addition and multiplication constitute an algebraic structure that approximates a field. It's not exactly, it doesn't satisfy all the field axioms, but it approximately satisfies them. And then this is what arithmetic is done. Arithmetic is done with the algebra of fields. But permutations, they bring all finite groups up to the size n into the computational algebra. So we have, in addition, we have n factorial unary operation on this algebra, and that is a very powerful addition to what we have when we compute with numbers. And I already mentioned that associative memory would be needed here, and it is an essential part of the architecture. It needs to be high capacity so that we can accommodate lifetimes worth of learning. What it basically does, it does nearest neighbor search among known vectors, and is also a major engineering challenge. But to try to understand how that kind of thing could be built, we are actually looking into the cerebellum as a model of an associative memory. And this goes back to the theory of the cerebellum by David Marr and James Olivets in 1969-71, when those theories were came. And this system of computing is complete. All traditional data structures, set sequences, list trees, stacks, can be represented and manipulated with the three operations. And so we can implement rule-based artificial intelligence. It's also, because of the high dimensionality, it is also good for learning from data, and so it's a complement to neural nets and deep learning. The computing is highly parallel, distributed, it's robust because of high dimensionality, it's also energy efficient. In that sense, it is brain-like. And it's we can think of it as a new computing paradigm for modeling cognition. It's compositional, it's programmable, and it's transparent. And it's an excellent fit for nanotechnology. Here are several examples where computing with high-dimensional vectors has been used. I will just go over them fairly quickly. Identifying 21 European languages. Training on each language took less than half a minute, and it involved about a million characters of data in each language. And the resulting vectors for the languages, they clustered based on language families. Romance formed a cluster, Germanic, its own cluster, Slavic, Baltic. Recognizing hand gestures, predicting the onset of a seizure, and this prediction was based on multiple EEG electrodes encoded into a single hypervector. Scene analysis, where a scene is encoded into what and where, in a way that we can ask questions of the scene about what is in such a position, or where is such and such in the example, letters and numbers were used. And semantic vectors, here's an early application, a random indexing for producing semantic vectors. The idea of semantic vector is if words have similar meaning, their semantic vectors should be similar in a vector space. And this random indexing, it's a fast and scalable alternative to semantic analysis, which is latent semantic analysis, which is based on singular value decomposition. Interesting that there's also actually a company that has been using this kind of actually based all its business on computing with high-dimensional vectors. They do text analysis, and the basic operation is random indexing. Company was founded in 2007, still doing well. Here are several contrasts that may help to sort of organize the space of computing and different alternatives. Comparing the traditional computing and rule-based AI, these computing with high-dimensional vectors, it shares the idea that you deal with structure explicitly. So the system is, in that sense, is transparent. And it's readily programmable. And it differs in that the objects are vectors rather than numbers. And this kind of computing is qualitative, probabilistic, rather than quantitative and deterministic. Compared to neural nets and deep learning, we share a high-dimensional distributed superposed representation and statistical learning, but differ in the sense that this neural nets and deep learning deal with structure implicitly, and they are known to be rather data hungry and opaque. Quantum computing, we share computing in superposition and differ in that we based on conventional physics and technology. And brains, well, share high-dimensional distributed superposed representation and energy. We can expect energy efficiency coming from this. And of course, different is that this is a product of engineering rather than evolution, and the overall capabilities are far below what brains do. Now, looking ahead, this computing with high-dimensional vectors can be regarded as a theory of computing for nanotechnology. And in that sense, a new computational paradigm. And it will be good for things like combining information from a variety of sensors and sources, and acting on the combined information, so we can expect to be developing and using this in sensor motor learning and semi-autonomous systems and robots. And also it combines statistical learning and rule-based systems, and so eventually I think language understanding will benefit from properties of computing with high-dimensional vectors. And I want to point out and thank for the support for this kind of work. In the 1980s, we had support from NASA. In the 1990s, it came from Japan's Ministry of International Technology and Industry. And since 2010, National Science Foundation, Semiconductor Research Corporation, Intel, U.S. Air Force Office of Scientific Research, and DARPA's Defense Science Office.